Hello friends, welcome back to the lecture series on high voltage engineering. We are going to discuss our next topic, that is DC resistivity measurement. So let us begin with the discussion. Here we have a resistivity, that is already I said in the previous lecture, given by the equation R is equal to rho L upon A. For this DC circuit, rho means resistivity is given by the equation resistance of the material, insulating material, multiplied by cross-sectional area of the material divided by length of the material. That is what the expression for the resistivity. So let us understand the methodology. For that purpose, we have to understand the construction of the electrode which we are going to use for the testing of the specimen. So as specimen, as you know, specimen is nothing but the a piece of that insulating material which we are going to use for in the power apparatus, maybe for some electrical circuit breaker, isolators, cable, etc. So that particular material which is to be used in the power apparatus have a piece, and that piece is going to be tested called as specimen, right? So the specimen shape and the electrode arrangement should be such that the resistivity can be easily calculated. So we have to do the calculation of that resistivity based on the particular specimen shape and the electrode arrangement. For solid specimen, the preferable shape is a flat plate. Means as we are going to use specimen maybe solid or liquid, right? So the preferable shape is flat plate with plane and parallel surfaces, generally circular. The specimens are normally in the form of disc of 5 to 10 centimeter diameter and 3 to 12 millimeter thickness. That is what the specimen diameter and the thickness, that is the size of that specimen. Now you can see if the electrodes are arranged to be in the contact with the surface of the specimen, the measured resistance will be generally greater due to the surface conductivity effects. Often, that is generally 3 electrode arrangement is used. That 3 electrode arrangement you can see in the diagram. Now these 3 electrodes are: first, unguarded electrode. Unguarded electrode. Second is guard electrode. And third is guarded electrode. Hence, this is called as a 3 electrode arrangement. The electrode which completely covers the surface of the specimen is called unguarded electrode and is connected to the high voltage terminal. That must be connected to the high voltage terminal. So this particular point or unguarded electrode must be connected to the high voltage terminal. The third electrode which surrounds the other measuring electrode is connected to a suitable terminal of the measuring circuit. So the width of this guard electrode must be at least twice the thickness of the specimen. And the unguarded electrode must extend to the outer edge of the guard electrode. The gap between the guarded and guard electrodes should be as small as possible. You can see here the space between the two guard and guarded electrode is very small. The effective diameter of the guarded electrode is greater than the actual diameter and is given as follows. Now, the diameter is shown here in the form of radius. So R1, R, and R2. So R1 and R2 and R be the radii of the guarded electrode, guard electrode, including the gap and the effective radius of the guarded electrode. Let the gap width be G and the specimen thickness is T. So you can see the specimen thickness is T. Specimen thickness is T. Okay, so this is your unguarded electrode, guard electrode, and guarded electrode, and in between that there is a specimen of thickness T is placed. Then we can use the equation from the reference R is equal to R1 plus G upon 2 minus delta, where delta by T is equal to 2 by pi ln cos hyperbolic pi g upon 4t. So these are the equations that we have to use. So here you can see this particular 3-terminal cell for the study of liquids, and this is called as a measuring cell. This is your 3-terminal electrode system. The measuring cell is generally a shallow metal box. So you can see there is a shallow metal box that is provided with insulating terminals. The box itself is connected to the guard electrode. So here you can see it is connected to the guard electrode. So this terminal of the box is connected to guard electrode and is grounded if the guard terminal is grounded. So if this guard terminal or guard electrode is terminal, a guard electrode is connected to ground, then this particular box is also grounded. Okay, so this is called a shallow metal box. Now the connecting lead for the guarded electrode. You can see this is the connecting lead for the guarded electrode is taken through a shielded wire. So this is your shielded wire. Shielded wire. In case the unguarded electrode means this one is grounded, the entire box is to be placed on insulated supports. So entire box, this particular metal box to be placed on the insulated supports and is to be placed in a grounded shield to eliminate the induced voltage, and the lead from the guard electrode is doubly shielded. Now, in the simple 2-terminal system, this is your 3-terminal cell for the study of liquids. Now, in the simple 2-terminal system, you can see this particular figure of 2-terminal system that is used for the measurement purpose. This particular terminal is high voltage terminal. High voltage terminal. And this is called as ground terminal. And here we have a insulating material of having thickness T. So there are 2 terminals used. One is this one and other is this one. Now, the measuring cell itself is the grounded support for the specimen, and a small solid wire is connected to the high voltage terminal. So this is small high voltage wire or small solid wire connected to high voltage terminal of the measuring circuit. Now this is a simple and compact arrangement for quick measurements and requires less skill. That requires less skill. You can see another arrangement. The arrangement used for the study of liquids that is shown in this figure, called as 3-terminal cell for study of liquids. Till this point we said the solid insulating material, as it is ground as it is the guard terminal and so on, right? So this is your solid material, which is to be tested by using this. Even the previous case of three terminal. Now, the arrangement used for the study of liquids is shown. This consists of outer cylindrical case and inner cylindrical case with a cylindrical guard electrode. With a cylindrical guard electrode. The opposing surfaces of the measuring electrode should be carefully finished to give a polished surface and a uniform spacing of about 0.25 mm. That spacing must be of 0.25 millimeter, and that is to be maintained. The insulation should be able to maintain the alignment of the electrode. Alignment of the electrode even at the highest temperatures used, and should still allow easy disassembling and cleaning. So this is one kind of a three-terminal cell for study of liquids, where we have a guarded electrode, unguarded electrode present, and here the liquid which is to be tested is placed. Here you can see whatever the liquid which we need to be tested is placed here. There is another arrangement which is used. Here you can see there is unguarded electrode, guard electrode, and guarded electrode. There is a hollow cylindrical electrode which is used. The liquid which is to be tested is placed here. The liquid which is to be tested is placed here. Definitely it is a oil. Then we have a metallic cylinder which is placed. Then there is a insulator spacer. Then there is a metal case or insulating case with a metal cover. This is also called as a three-terminal cell for the study of liquids. This is another kind of three-terminal cell for the study of liquids. So this is another simple arrangement of three electrode system. This consists of a metallic cylindrical container. Metallic cylindrical container. This is just like a container with concentric hollow cylindrical electrodes as guard and guarded electrodes. As guard and guarded electrodes. The inner surface of the container electrode, that is unguarded electrode, and the outer surface of the guard and unguarded electrode should be carefully finished, and a clearance of about 0.25 mm to 0.5 mm. 0.25 mm to 0.5 mm should be accurately maintained. The arrangement requires less liquid, and it is only of 1 to 2 ml for testing a whole volume of the oil. Okay, so now this is all about the constructional parts of these testing circuits or kits which are used. Now let us understand the measuring circuit. Here you can see that test specimen which is placed here. So let us understand this circuit. Here we have a battery source, that is DC stabilized power supply, that varies from 500 to 2000 volts. So it means 0.5 kilovolt to 2 kilovolt. Here there is a voltmeter, that is a measuring device which is placed. There is a galvanometer of 10 to the power minus 8 to 10 to the power minus 9 ampere per centimeter deflection. Then RSH is the shunt resistance, and the resistance or the resistivity of the material which is to be tested is of this specimen. So this is called specimen. Here we have a switch connecting point 1 and point 2. Point 2 be the grounded terminal. So B, we can switch which toggle between point number 1 and point number 2. So now let us understand this circuit. A simple measuring circuit for the measurement of resistance is shown in the figure. The galvanometer is first calibrated by using a standard resistance of 1 to 10 megaohms. So your first step is to calibrate the galvanometer of 1 to 10 mega ohm. And there is a like a value that can be changed. Accuracy say plus minus 0.5% or plus minus 1%. Now, if necessary, a standard universal shunt is used with the galvanometer, which is already shown here, connected across the galvanometer. The deflection in centimeter per microampere of current is noted. So this does the notation of that particular value. Now the specimen RP is inserted in the circuit and maintaining the same supply voltage, the galvanometer current is observed by adjusting the universal shunt if necessary. The galvanometer gives a maximum sensitivity up to 10 to the power minus 9 ampere per centimeter deflection, and a DC amplifier has to be used along with the galvanometer for higher sensitivities. So if the sensitivity to be increased, then the DC amplifier to amplify that can be used. Now the resistance of the specimen is given by the equation Rp is equal to V upon D into G, where D is deflection in centimeter with specimen. There must be a specimen used, right? So this is specimen, and G be the galvanometer sensitivity. Galvanometer sensitivity. This G can be given by the equation V upon Rs into 1 upon N into 1 upon ds. So this particular circuit can be used where N with the universal shunt ratio, ds with the deflection in centimeter with the standard resistance in position, Rs is the standard resistance used for calibration, and V be the supply voltage. It may be noted that the deflection with the specimen in the circuit will change with time. The initial high deflections indicate the high charging current required by the dielectric specimen. So dielectric specimen, insulating specimen, which is placed here. For the purpose of calculations, the steady current obtained after a considerable long charging time should only be taken. Switch B is used to discharge the specimen after the measurements are complete, and as well for the initial discharging before the measurements are undertaken. So first that switch to be placed on position 1, the supply voltage must be given to the specimen and it is to be measured with the help of galvanometer where the shunt resistance is placed. That specimen to be grounded here. At this point that must be grounded. This end is also connected to ground. The voltmeter end is also connected to ground. So voltmeter basically does the voltage measurement. This galvanometer does the measurement of the specimen, right? So this gives the sensitivity which is noted here. Now after the specimen testing, that B can be placed at point 2 so that the specimen can get discharged. So this is what the charging of the specimen for the testing purpose when the switch is at position 1. So this is for position 1. And when it is done, the position 2 connection make that discharge of the specimen to the ground. So the initial discharging before that is already set. So therefore we have this particular discharge. Now there is another figure that can be preferred you can see this. This is where, as I already said in previous discussion, the DC amplifier can be used for the extension purpose, so that the range of 10 to the power minus 8 to minus 9 can be increased from that is increased to 10 to the power minus 12 to 10 to the power minus 13 ampere per centimeter. Ampere per centimeter. And this can be done by using the DC amplifier. The arrangement is same. There is no change, where you can see that E be the stabilized power supply of 0.5 kilovolt to 2 kilovolt. V be the voltage measurement device, that is voltmeter. RP be the specimen, the testing specimen which is kept. RS be the standard resistance, and this ES dash with the auxiliary source that is given to the circuit. So this particular figure has the DC galvanometer, but it is replaced by a DC amplifier. So here you can see that DC galvanometer, the previous figure, and it is replaced by a DC amplifier for resistivity measurement. Here the DC amplifier is used as a null detector. A separate potentiometer circuit is used for obtaining a signal E equal and opposite to the voltage drop across the standard resistance RS. Across the standard resistance RS. At balance, the voltage drop across RS is effectively made 0. So that voltage drop is to be made 0. Any AC voltage appearing across the standard resistance RS is amplified only by the net gain of the amplifier, which is small. Using recording meter after the DC amplifier in this arrangement, the volt ampere time curves for long durations of the order of several hours can be obtained. So this information is essential to determine relaxation time at low frequencies or with DC. So this is what one kind of DC amplifier circuit. This is Wheatstone bridge arrangement that is also used, and one of the resistances RA is made variable for balancing the bridge. Here RA must be used to balance the resistance. See, the arrangement is same. Here you have a switch. Switch is placed at position 1 whenever you need to test the specimen for the resistance, right? And these are already said that guarded, unguarded, and guard terminals. So we have these 3 terminals. Right? So these 3 terminals, which are already shown in the previous diagram, that is unguarded electrode, the first one, the guard electrode, the lower one, and the side one is the guarded electrode. So these are shown here. And we have this balancing resistance RA that balances, and therefore it is called as Wheatstone bridge. Now at balance, RP is given by some equation that with the specimen arrangement used, the volume resistivity rho can be given as, or you can say that specimen rho is equal to R into pi radius square divided by D ohm meter. R is measured resistance. R is measured resistance, that is in ohms. T with the thickness of specimen. Thickness of specimen in meters, and small r with the effective radius. Effective radius in meters. So using this network, the volume resistivity rho for liquid specimen with cylindrical electrodes can be measured, right? So this is what all about the DC resistivity measurement. DC resistivity measurement. All the required figures related to the solid specimen and liquid specimen testing circuits are discussed. The required circuit for the measurement is also discussed. Hope you understood the concept related to this particular topic. So the name of the topic is DC resistivity measurement. So thank you so much, guys. Take care.